Hi, I'm Ben Vogel. This is Jason Marchese and Bahar Haydari. We are third year electrical engineering students at the University of British Columbia, Okanagan campus, and we were assigned a project to use the Texas Instruments Launchpad to solve a real world issue.
The issue we decided to face is air pollution. Air pollution is a very large issue currently. Specifically in the Okanagan, we face dangerous levels of carbon monoxide in particular, usually caused by forest fires in the summertime and fuel emissions all year round. In other parts of the world, there are even more devastating levels of air pollution, so the device that we have come up with can be applied anywhere in the world. Our device helps at-risk individuals, and it also helps people who want to make a difference in the world. Talking about the solution is Jason.
Our device will implement 4 different sensors, and this will measure the ppm value of different air qualities and display this on an LCD screen. This will allow these at-risk populations to understand the dangers of the air quality in their locations. This solution can be implemented in a few different ways. If we can alternate our current program so it can be running continuously to model the air quality over a long period of time to be analyzed by the individuals to know when it is safer for them to be outside if the air quality is too bad.
At the heart of the device is a Texas Instruments Launchpad microcontroller, which is located here. This board handles the task of reading the sensors as well as outputting data to the LCD screen. Our hardware design is put together in such a way that many components are modular. This allows the user to utilize a multitude of different sensors in order to customize the operation of the device in an easy way. In its current configuration, the board is outfitted with carbon monoxide, hydrogen, and methane sensors, as well as a general air quality sensor. All of the components of the device operate on 5 volts, so the board is equipped with 4 Texas Instruments LM1084 voltage regulators located at the back here. By using voltage regulators, the device may be operated on a range of voltages. The LCD screen is capable of displaying 2 rows of 16 characters. The top row displays what gas the device is currently sensing, and the bottom row displays the concentration of the gas in parts per million. A push button located here on the device is used to cycle through the 4 gas sensors. Once the device makes it out of the prototype stage, the wiring will be drastically cleaned up and all the hardware will be placed into an aesthetically pleasing enclosure.
Our code is split into 4 main parts. There's the initialization section, there's the void setup area, there's the functions, and then there's the main loop. To start off the introduction, in initializations, we have introduced the global variables to be used throughout this program. And then in the main setup, we have set up the various pins to be used for the function on the board, various functions on the board. We have outputs and an input. We then have these main functions we use in our main loop, which will be discussed later. And this is our main loop. We have a while loop that cycles. When one cycled through, it will check that the button is high, and then it will increment the counter, which dictates which sensor is being read. It reads the sensor, calculates the ppm, and prints the corresponding sensor and the ppm value. Save this and then 40 milliseconds before doing the same, before checking if the button is pressed high again. When I press this button here, it cycles through the different air quality sensors and displays them on the computer screen. There's also this green LED that lights up because the air is safe to breathe.
The code is comprised of a few subroutines and a while loop. In the while loop, the subroutines are all called, and I will be discussing these subroutines. The first subroutine performs the analog to digital conversion and reads the sensor. Every time the button is pressed, the counter is incremented and a different sensor is read. The second subroutine does ppm calculations by using the value that was read in the previous subroutine and various formulas, as demonstrated here. The third and final subroutine controls the LEDs. If the ppm level is between certain values, a different LED will turn on. These values were selected after conducting some research. If we had more time, we would have liked to do more research and converted all of the ppm values to Air Quality Index or AQI values. AQI was developed by the Environmental Protection Agency, EPA, to provide accurate, timely, and easily understandable information about daily levels of air pollution. The only challenge that would arise with this is all pollutants have a different ratio when converting from ppm to AQI. So research would have to go into what level of ppm can be converted to a certain level of AQI. For example, the ratio for the conversion from ppm to AQI for carbon monoxide is 1 ppm is equivalent to 11 on the AQI scale.